So now that you have a grid created, it's time to start filling its attribute data. And the first attribute is elevation. So I'll start by finding and loading the elevation file. Our elevation file is an elevation raster. I'm going to pick it up, click it, drag it, and drop it onto the map. Now note that it was positioned right over my computational domain layer, and that's because that was my active layer. So be careful about what layer is active before you load data. I want to pick it up with my left mouse click and take it and drop it into the external layers group, or you can make a new group for it called elevation. Right click, add a group, elevation. Whoops, that's not how you spell elevation. Right click N to rename it, elevation. And then you can move it here. Note it disappears if you turn on your raster, or excuse me, if you turn on your satellite raster, so keep that always on the bottom. And minimize that, and we will zoom out so you can see the extent of our elevation raster. This is a LiDAR raster, so if I double click it and I go to information, you can see that this raster has a coordinate system that matches our project coordinate system. That's not super critical, but it does have, but it is in feet. It is in its horizontal units are in feet and its vertical units are in feet. The vertical units are important. And the pixel size is 1 foot by 1 foot. And if I go to symbology, I can set it from single band gray to hillshade, and I can set the Z factor to 2 and click apply. Now this will help you find physical features on your map by using hillshade. Now if you set this to 1 and click apply again, you'll see that it's much more muted. So by setting it to 2, we make those elevations really pop out. If you're having trouble finding something, say like the channel bank alignment, you can also change the azimuth of the light and apply a correction to the azimuth of the light. And that is how you style a high resolution elevation raster. Low resolution elevation raster might be better to keep it in grayscale because it doesn't look very nice like this when you set it to hillshade. It can actually make it harder to find things. When we zoom in to the individual grid level, this is a grid element number 1, and as you can see here, grid element number 1, and this is the elevation I already interpolated to it the first time that I set my elevation data. And so you can see what it's happening is it's getting a weighted average elevation of every pixel that is within or near or intersected by this grid polygon. So if you click this elevation button right here, this source raster goes to your elevation. The no data, we don't really need a no data, but you still have to assign it. But we don't need to fill no data because we have complete coverage. So this is our source no data. We don't need to use multiple thread, doesn't really do much, doesn't really help even when you have a really huge project, so don't bother with it. And this becomes the average of all non-no data pixels, and I click OK, and we are now calculating an area weighted average of any pixel intersecting this grid element. It's going to actually warp this into a new raster that has a 30 foot by 30 foot and is perfectly aligned to our grid, and then it's going to sample the center of that grid. Using the centroid is going to sample that new raster, and that raster was a temporary layer and has now been deleted. If you want to see what that elevation looks like, the difference in a 1 by 1 raster and a 30 by 30 raster, you're looking at this right here. So this is a 1 by 1 raster, and of course the original is 1 by 1 compared to 30 by 30. Now you might say, well, if you have a 1 by 1 raster, why are you not using a 5 by 5 cell size or a 10 by 10 cell size? And it is specifically due to two major issues. One being that you might have too much water for a grid cell size that small. So if you have a large hydrograph or a large collection of water in your system and you're using a very small grid cell size, that's going to mean a very small time step. So it's going to slow your project down and possibly cause instabilities in your project area that you then have to slow the project down even more to correct instabilities. Also, if you work on a project like this and you have your grid cell size, you are going to quadruple your total number of grid elements. So the smaller your grid cell size, the larger your project, the larger it takes to run, the larger it takes to set up this complex urban scenario, and the larger it takes to review. So that's costing you time and money. So why, rather than trying to get the perfect small grid cell size, stay with the larger grid cell size. It gives you really good data for 20 foot by 20 foot urban project, and then you don't waste money and time trying to get a 10 by 10 or 5 by 5 grid size perfect, and it is very time consuming. So 20 by 20 is what we recommend for urban modeling, 20 foot by 20 foot. Alright, I think that's about it, so let me turn this off and I can now save the project again. And now when I save this, I'm going to click yes, and again this layer of data is going to be committed to the geo package, because, and that's why it's taking longer to save it, is because it's writing this elevation data to the geo package. Now, and as you can see, it also put it in external layers because that's its function. It's designed to do that. So I'm going to move it back here because that's where we want it. And then I will minimize that, and we can turn it on and off as we need it. And now I'll save this again, because when anytime that you move or change something in here, that save button, or excuse me, that unsaved status is indicated by that asterisk. So I think that's it for this video. The next thing we'll do is interpolate and value data.